Okay, next we'll take a look at a very important thing to be able to do with a function, and that is finding the average rate of change between 2 points on that function. And I'm going to begin with sort of an application to see where we might use this. And so we're going to suppose that s of t is the function that gives the distance traveled, s, in miles. So we travel s miles, t hours into some trip that begins at noon. So suppose we go out on a road trip. The road trip starts at noon. After t hours pass, s of t is the function that tells us how far we've traveled. And so we have these values here. S of 0 is 0. So of course at noon we've traveled 0 miles. We haven't began the trip. S of 1 is 50, so after 1 hour we've traveled 50 miles. S of 2 is 75, so by 2 p.m. we've traveled 75 miles. S of 3 is 140, and S of 4 is 200. And our graph of S of t looks like this. So our y-axis, that's S in miles, that's how far we've traveled. Our x-axis, I shouldn't call them y and x, the vertical axis is S, and the horizontal axis is t, how much time has passed. And the path that we're taking looks like this. Now, for this particular setting, the rate of change between 2 points, that's telling you how S has changed with respect to t. So how many miles you've traveled over a certain amount of time. Now, if you think of distance in miles and time in hours, the rate of change between 2 points is telling you how many miles per hour we've traveled on that interval. So basically, that's your speed. Okay, and rates of change. You study slopes quite a bit. Slopes are just giving the rate of change of a linear function, and rates of change are a very important concept. This is a very good application of it. If we're talking about distance over time, then the rate of change is your speed. But there are numerous other applications where we have some function, and we want to talk about the rate at which that function is changing. So this is going to be a very common thing to study. Okay, so the slope of the line between any 2 points yields the average speed on that interval. So basically, if I took a line between, say, t is 1 and t is 3, and I'll construct a line through those points, whatever the slope of that line is, m would be the average speed between 1 and 3. So it would tell us between 1 p.m. and 3 p.m. how fast we were going on average. Of course, it wouldn't tell us how fast we're going at any particular moment in time. We call that the instantaneous rate of change. But it would, again, just give us an average. So let's calculate that for a couple different cases. Suppose we wanted to find the average speed between 1 p.m. and 4 p.m. So again, that speed is the distance traveled over time. And the way we could construct this is if we take the distance that we've traveled at 4 p.m. and subtract the distance that we traveled at 1 p.m., that would tell us how far we traveled between 1 and 4. And then we divide that by 4 minus 1, that would tell us how long we traveled between 1 and 4. And that would give us that average speed. So let me go back up and look. At 4 p.m., we traveled 200 miles, and at 1 p.m., we traveled 50 miles. So what I'm going to do to construct this thing is I'm going to take 200 miles minus 50 miles. And again, this is 50 was distance at 4, or I'm sorry, distance at 1 rather, and 200 was the distance at 4. And the difference of those things then tells us how far we traveled between 1 and 4. On the bottom, I'm going to subtract, we traveled for 4 hours minus 1 hour between 1 and 4 p.m. So this tells us how long we were traveling for. So that numerator of 200 minus 50, that would give us 150 miles. That's how far we traveled on that interval. And 4 hours minus 1 hour, that would give us 3 hours. That's how long we were traveling for. And 150 divided by 3 is 50, and this would be in miles per hour. And again, this would be giving us our average speed. Now, that 250, notice that was f of 4 and f of 1. F of 4 was 200, f of 1 was 50. So another way of thinking about this, and I'll do it for a different example, if I want this average speed between 2 p.m. and 3 p.m., instead of just skipping right to however far we traveled at 3 p.m., we could just call that f of 3. And how far we traveled at 2 p.m., we could call that f of 2, and do that over 3 minus 2. And notice what we're doing right now is just calculating a slope, right? Remember that general slope formula, y2 minus y1 over x2 minus x1, giving a slope? That's all this is. The f of 3 and f of 2, that's your y2 and y1. And the 3 and the 2, that's x2 and x1. What we're doing is we're finding the slope of the line between the points where x is 2 and x is 3. So if I go back up to my picture between 2 and 3, if I connected those, try a little bit better there. If I connected those with a line, the slope of that line is what we're calculating here to find the average speed between those 2 points. We call those lines secant lines. All right, while I was up here, I should have found f of 3 and f of 2. Okay, so let's see here. 3 was 140, 2 was 75. Okay, so this is going to be 140 minus 75 over 3 minus 2, which is 1. 140 minus 75, that would be 65 over 1, so just 65 miles per hour. Okay, so that was our average speed on that interval. All right, so we just want to extend this to any function. So, generally when we're dealing with some random function, we don't necessarily know what that function represents. It could be a function of, profit over time, or production, or, distance, as was this case. Our functions could represent anything. But that rate of change is basically telling you, a speed, or how fast something's growing or shrinking, or, basically just how something's changing. Okay, so as a general definition, we say the average rate of change of the function y equals f of x between x equals a and x equals b is given by exactly what we wrote out in that last example, f of b minus f of a over b minus a. This value is the slope of the secant line between the points a f of a and b f of b. So again, just to generalize this, if I have some graph f of x, so here's some function f of x, and I pick 2 points. Let's say right here this is x equals a, and up here this is x equals b. Then f of a is the y-coordinate at the first point, and f of b is the y-coordinate at the second point. So what we're accomplishing with this is we're taking the line between those 2 points. Oops. There we go. Oh boy. Third time's the charm. All right, good enough. All right, so we're taking the line between those 2 points, and we are finding the slope of that line. So m would be the difference in the y's, f of b minus f of a, over the difference in the x's, b minus a. And again, this line we call a secant line. All right, so let's look at a couple of examples. Suppose we wanted to find the average rate of change of the function f of x is x minus 3 squared between x equals 1 and x equals 3. So what we're going to do is take f of 3 minus f of 1, and then divide that by 3 minus 1. So f of 3, that's just going to be take the function and plug in 3. That's actually kind of nice, right? If I plugged in 3 to this, I'd have 3 minus 3, which is 0. 0 squared is 0. Minus 1, so if or f of 1 rather, so if I plug in 1, I'd have 1 minus 3 is negative 2. Negative 2 squared is 4. Over 3 minus 1, which is 2. So this gives me negative 4 over 2, which is negative 2. Okay, for another example, let's say x is 4 and x is 7. So we would take f of 7 minus f of 4 and divide that by 7 minus 4. So f of 7, that's going to be 7 minus 3, so 4 squared. Minus f of 4, that would be 4 minus 3, so 1 squared over 7 minus 4, which is 3. So I have 16 minus 1 over 3, so 15 over 3, which is 5. Okay, so to find the average rate of change between 2 values for x, we're just plugging those values into the function and subtracting that, and then dividing that by the difference between the values themselves. Again, this is giving us the slope of the secant line. That's just the line passing between them. Now, one generic average rate of change we might look at is something called the difference quotient. And as a definition, the difference quotient of a function f is given by f of x plus h minus f of x over h. Now, what this is really doing is, again, we're taking some generic function f, we're picking some point, calling that x on the x-axis, and then we're moving over some distance h, and that puts us at some other point, x plus h. That would be right here. And then we're just finding the average rate of change between those 2 points, giving the slope of that secant line. When we subtract the numerators, or the y-coordinates rather, we have f of x plus h minus f of x, and on bottom we'd have x plus h minus x, which simplifies down to just h. This is going to end up being a very, very important concept when you move on to calculus. The basis of what we call the derivative, which is the bulk of what you're going to study in a first course in calculus, is really just a difference quotient. So this is an important thing to be able to find. So let's take an example. Suppose we wanted to find the difference quotient of f of x is equal to x squared. And again, in general, this is f of x plus h minus f of x over h. So f of x plus h in this case, we're replacing the x with x plus h, so instead of x squared, we'd have x plus h squared, minus f of x, which was just x squared. Again, this is over h. If we expand out that x plus h squared, we'd have x squared plus 2xh plus h squared minus x squared over h. So the x squared and the negative x squared cancels. That leaves us with 2xh plus h squared over h. And now we can cancel a factor of h from each term, which leaves us with 2x plus h. Okay, in this 2x plus h, we say that is the difference quotient of f of x is equal to x squared. And again, basically, this is giving us the average rate of change between some point x and some point a bit to the right of that x plus h.